being produced by magnetic effects. Okay? And the concept is called as the concept of electromagnetic induction. Now when you talk about electromagnetic induction, you must be knowing a scientist by the name Sir Michael Faraday. 1831, he performs an experiment with the magnets and the coil and comes up with a totally different branch of physics called as the electromagnetic induction, in which he explains that whenever magnetic field changes, it has a tendency to produce electrical effects. Fine? So what he did and how he did that, we'll try to understand it from the simulations today. So first of all, what I have with me is a bar magnet. I hope you know what is a bar magnet. Have you used a bar magnet before? Yes or no?
Yes.
It looks like this. It has a north pole and a south pole, right? Isn't it? But you need to understand that this magnet modifies the space around itself. And that modified space, like in case of the charge, we call that as the electric field. Here it will be called as the magnetic field. Is that fine? If you remember from electrostatics, we discussed that the electric field lines start from the positive charge and terminate at negative charge, isn't it? Here, if you talk about the same thing, if there is a magnet, say for example, it has a strength, it has some strength. So the field lines will start from the north pole and terminate at the south pole like this. See, this is how it works. From the outside, you are seeing the orientation, is it? See, if you want to check the direction at any point, for example, I want to check the direction here.
Close.
I want to check the direction here. See, the red pointer, it is going here, right? So that will give me the direction of the magnetic field lines everywhere around this bar magnet. So remember, the bar magnet modifies the space around itself, and the modified space will be called as the magnetic field. And the magnetic field can be shown like this. See, if I bring a strong magnet, you will see more field lines. See, do you see more number of lines that can be drawn from the north pole to the south pole? Yes. If I decrease the strength, see, they'll fade away, right? The strength is 15% and you're seeing less number of field lines. But when we have a strong magnet, strong means its strength is more. See what is happening? More number of field lines are visible, isn't it? Is that clear? When there are more number of field lines, remember the flux is more. What is flux? Flux is the number of field lines crossing your area. Is that fine? If more number of field lines are there, we say flux is more. If less number of field lines are there, we say flux is less. Is that fine? Okay? And this flux, we represent this flux by phi. And this phi is equal to the magnetic field times the area. Remember this thing for the flux. Okay? What is flux? The number of field lines. Okay? The number of field lines that are crossing. Fine? If the number of field lines are more, then we have more flux. If the number of field lines are less, then we have less flux. When there is stronger magnetic field, flux will be high. When there is weak magnetic field, the flux will be less. Is that fine? So we have a bar magnet. The field lines, remember, start from the north pole, terminate at the south pole like this. Similarly, in case of the charges, they started from positive and terminated at negative, isn't it? But the difference that you see, very important, the difference that you see between the magnetic field lines and the electric field lines is that when you talk about the magnet, the field lines from the outside run from north to south, okay? Something like this. Something like this, okay, something like this. So north to south. If I talk about charges, for example, there is a positive charge and there is a negative charge. If I have to show the field lines, how did I show them? Last class, yes? Were there something like this? Yes?
Yes.
See, every time they were from positive to negative, isn't it? Yes or no?
Yes.
But here there is a difference. The difference is that if you want to show the field lines inside the magnet, then the direction is opposite. They run from south to north. They run from south to north like this. So they form closed loops. And that is the reason you will not have a north pole. You will not have a south pole in isolation. They are always present in pairs. Is that fine? They are always present together. If you break a magnet, see, I'll show the field inside. See? But just wait, I'll show that after this. I'll have to close this. So, very important thing here, that even if you break a magnet, for example, there is a magnet and you break it. So, it has two parts now, right? Now, if you break it into parts, this was north, this was south. Do you know what happens? This again develops north and this develops its own south. Why? Because the magnetic field lines are closed curves. They are what? They are what?
Closed curves.
Closed curves. Outside they run from north to south, inside they run from south to north. But in case of charges, see, there is nothing like that. They always start from positive, they always terminate at negative, no matter where. Fine? This is the difference. This is a magnet. So if the strength of the magnet is high, then you will see more number of field lines. If the strength is less, then you will see less number of field lines. Now if I ask you a question, what is flux? The number of field lines. Tell me, where is flux more? Is the flux higher here or is the flux higher here? Where is more flux? Where do we see? Where do we observe more flux? 1 or 2? Exactly, at 1. Why? Because the number of field lines crossing they are very close. So the number of field lines are high, and therefore remember, when you go very close to a magnet, you might have observed more repulsion or attraction, isn't it? When you go away, less repulsion or attraction, isn't it? So that is the difference. So if I just click a picture of this first, so because I have to erase this and I have to show you the direction of the field lines inside as well. Click. Yes? Okay, now see. See the direction of the field lines. If I try to rotate it anywhere, see, I take it, wherever I take it, it will always point in the direction of the magnetic field lines. This is the compass. Okay? The compass will always show you the direction, no matter where you place it. Say for example, I place it at the top. It is always aligning itself along the direction of the magnetic field line. If I place it, say for example, I place it at the center, somewhere here. See the direction? This is north, magnetic field line goes like this, isn't it? So the red is away. If I take it here, red is towards this because north is there, south is here. Is that fine? Is that clear? That is the concept of your bar magnet and the space that it modifies around itself. See, here the magnetic field is straight. That means north, the magnetic field line has this direction. It will go like this. If I place the same somewhere here, see, the magnetic field line is like this. It is going like something like this. Is that fine? So the direction of the magnetic field lines starts from the north, terminates at the south, but outside. But inside, it starts from the south and terminates at north. Is that fine? Due to which they are always closed curves. That's it. Fine? Now, Michael Faraday, you know this Michael Faraday? He was working at a shop and the shop was of a book binder. This guy, at the age of 21, had already started publishing papers. He did not go to a university or anything. What he did was, at the bookbinder shop, people come and give books for the book binding, isn't it? Do you know what he used to do? He used to read all the books that he got, and he got knowledge from those books. And then he became the student of a professor at that time known by the name Professor Davy. He got the information, and then when he wrote a letter to Professor Davy, and he told him that I have read all these books over the period of time. I have knowledge about things, and I know you do things like that. So can you please help me? He said, okay, come. You will work with me as a laboratory assistant, Michael Faraday. And you know how much work he has done? Faraday's laws here, Faraday's laws in chemistry as well. Michael Faraday was the reason your Teslas are working. Fine? Now what this guy did, see what he did. He performed a famous experiment in which he found that this magnetic field has the tendency to produce electricity. This magnetic field has the tendency to generate electrical effects. So how he did that? The experiment was based on a coil, okay? And through this coil we had a bulb which was connected, and then there was a bar magnet, the same bar magnet that I just showed you, okay? Let me keep the strength of the bar magnet at 50%. Let me take less number of coils here. Let me take a bulb, and then I can increase the area or decrease. Let me keep the less number of electrons. Okay, fine. Now see, if I ask you a question, this is the magnetic field. This is a bar magnet which has a magnetic field something like this, and you know what is the direction. What is the direction? Yes. What is the direction of the magnetic field lines? From north to south, isn't it? Like this. This is the magnetic field line. From north to south. And inside it is from south to north. Is that fine? Now this magnetic field which is being generated by the bar magnet, these magnetic field lines have magnetic flux. That is the number of field lines, isn't it? So what Michael Faraday is doing is that, see what he did? The first part that he did was, he tried to move this bar magnet towards the coil. Tell me, is there any battery connected with this coil? No. Is there any source which can lit up this bulb? No. There is nothing, right? But if you do this, see, if you move this bar magnet towards the coil, the first thing that he observed was, when he, see what is happening? When he is taking the magnet towards the coil, see, there are electrons running in the coil, isn't it? Yes? The electrons are moving. And the bulb is glowing. Is that fine? When he is taking the bar magnet towards the coil, the bulb is glowing. Although there was no battery connected to the coil. See, when the bar magnet is at rest, nothing is happening. But when this bar magnet is going towards, you are seeing that the bulb is glowing. Okay, if I replace it by the emitter, see what is happening here. When I am taking it forward, the deflection is towards the left, isn't it? Yes? And if I reverse the polarity, if I go like this, see, and I increase the number of turns, see what will happen? More. See, the deflection is towards right when I am going back, and the deflection is towards left when I am going forward, isn't it? So the deflection, the direction of deflection is also changing. And that means there is current, there is voltage, which is, this is actually a voltmeter which is connected to this coil, okay? So what is happening is that he is observing that whenever the magnet is in motion, and this coil always shows, the bulb always glows, okay? But if he kept the bar magnet at rest and he moved the coil, see, now he is moving the coil, see? Again the same thing is happening. When the coil is being moved, the bulb is glowing again. But when the coil is at rest, there is no glowing. It is only when the bulb is taken away or brought towards the bar magnet, when the coil is taken away or brought closer, when there is motion of the coil, then only the bulb is glowing. When the bulb is kept or the coil is kept at rest, nothing is happening. Similarly with the bar magnet. So he is observing that whenever there is a relative motion between the bar magnet and the coil, this bulb is glowing. But this bulb will only glow when there will be voltage, isn't it? When there will be battery connected. There was no battery connected. So what is causing the bulb to glow? What is the cause? Yes? Anyone? Can you tell me what do you observe? What is happening? I told you, I showed you the two parts. First part, when the bar magnet is moved. See? When the bar magnet is moved towards the coil. See? When it is kept inside, the magnetic field would have been the maximum, isn't it? But then there is no glowing. But when you take the bar magnet away, again glowing. When you take it inside, keep it at rest, nothing is happening. Yes?
Maybe because of the movement.
Because of the movement, what is happening? It is because of the movement. We are seeing that the bulb is glowing only because when there is movement, isn't it? But the question is why? Why? What is happening due to movement? The magnetism moves the electrons. Anything else? See, if I move the coil, again the same thing. See? Isn't it? So whenever there is relative motion, write it down, the first point that you will write. The first point that you will write. Observations. When the bar magnet is moved towards the coil or away from it, when the bar magnet is moved towards the coil or away from it, when the bar magnet is moved towards the coil or away from it, the bulb glows. This is an observation, isn't it? The bulb glows. Okay? Point number 2. Point number 2. When the coil is taken away or brought closer, the bulb again glows. When the coil is taken away or brought closer, the bulb again glows, isn't it? See? The bulb is glowing when there is motion. When there is no motion, the bulb is not glowing, isn't it? You keep it at rest, nothing is happening.
But it is taken away.
When the coil is taken away or brought closer, the bulb again glows. Fine. Third point. When both are at rest, nothing happens. When both are at rest, nothing happens. So these are the observations, okay? Third, when the coil is kept, see here, the magnetic field inside the coil is maximum, isn't it? It is very close to the magnet. But even when the magnetic field is maximum, nothing is happening. There is no glow. Okay? So what was the reason? What is happening? What did you write? When the coil is kept?
No, last thing I wrote is when both are rest, nothing happens.
Nothing happens. Fourth point, when the coil is kept inside the magnetic field, the bulb doesn't glow. The bulb doesn't glow. Okay? So these were the observations. Now he has to conclude something from it. What do you conclude from it? Someone said it is the electric field, it is the magnetic field which is causing the electrons to flow. Any other observation that you can come up with? Any other conclusion that you can come up with? What do you observe? What do you think? Why is the bulb glowing when there is motion? Am I compelling the electrons to move? No. isn't it? Yes? What do you think? And you will observe a pattern as well. See, one important pattern that you have to observe here. If I take the bar magnet away and bring it back, the direction of the electrons is changing, see? Yes? Yeah.
What is the changing magnetic field which induces the current?
The changing magnetic field is inducing the current. How does the magnetic field change?
Because of the electrons.
Because of the electrons?
Movement causes the electrons.
See, observe one thing, observe something here, see? When the magnet is taken from left to right, what is happening? See the motion of these electrons, see? Is it anti-clockwise? Yes? Counterclockwise? Yes or no? But when the same magnet, see what is happening, very important. What is the motion? Counterclockwise? But when I am going away, see what is happening? Now it's clockwise. Do you observe this? See, very carefully observe it. When I am taking this bar magnet towards the coil, the direction of the electrons is anti-clockwise, isn't it? But the moment we go out, it is clockwise. And then again, one important thing. When I am going back inside, it is counterclockwise. And when I am taking it out, again it's clockwise. So the direction of the current which is going through this coil is also changing. So Michael Faraday is trying to observe all this and come up with some conclusion. So what conclusion does he come up with? See what he observed. I'll try to explain what happened actually, okay? So Michael Faraday knew that this bar magnet has its magnetic field, isn't it? And if you know the magnetic field is from north to south, is it? Yes? And inside it is something like this. Okay? So what he observed was, when there is a motion, the bulb glows. Why is that happening? So what he concludes, he says, when the bar magnet was away from the coil, the number of field lines which were linked, which were going into this, are less, isn't it? See, when this magnet is away, the number of field lines which are here is less as compared to the number of field lines when this bar magnet is going towards it. If I show the magnetic field like this, for example, tell me, is the flux here more or less as compared to when I am taking the magnet towards the coil? Will the flux through this coil increase? Yes? When I am taking this magnet towards the coil, the flux through this coil will increase. More number of field lines will pass through the coil, isn't it? When I am taking this bar magnet inside, the number of field lines which get linked with this coil increases, isn't it? See, if I show it here, again with the help of the diagram, see, the field lines here are very faded, but when I take it inside, see what is happening. Are they getting more prominent? So when they are getting, see, again it is at stop, nothing is happening. When they are increasing, the prominent means they are getting more dark, they are getting linked with the coil. So Michael Faraday comes up with a conclusion that whenever the flux which is linked with the coil changes means here it was less, initially it was less, okay, but now what is happening, it is increasing, see, it is increasing, fine, it reaches a maximum value, and then when I take it out, see what is happening when I take it out, they are fading away, isn't it? Fading means again changing, right? So he is saying, When the flux which is linked with the coil, increases or decreases, that means it changes. That only has a tendency to produce EMF, and that EMF causes the bulb to glow. So he comes up with a law called as the first law of electromagnetic induction, that magnetism can produce electricity. How? So the point is, write it down. Observation you wrote, now write the conclusion. Whenever the flux linked with a coil, changes. How does it change? Can you tell me how does it change? Yes? First it was by the motion of linked with a coil changes. Whenever the flux linked with a coil changes, okay, an EMF is induced in the coil. An EMF, electromotive force, an EMF is induced in the coil. EMF. An EMF is induced in the coil. An EMF is induced in the coil, electromotive force. Okay, due to which the bulb glows. Is that fine? This is the conclusion. So, how does this flux change? There were three ways in which it was changing. First, when he was moving what? The bar magnet, okay? When he was moving this, the bar magnet. When the bar magnet is being moved, he is seeing that, see, more number of field lines are getting linked, less number of field lines are getting linked. So flux is continuously changing through this coil. When the flux is changing through this coil doesn't like the change. It is like a person. For example, you people. In the morning you are asleep. You know Newton's first law of motion? What is that? A body head continues to be in the state of until and unless an external force tries to change its state, isn't it? Similar thing happens everywhere. Like in the morning you are asleep. A body sleeping continues to be in the state of sleep until an alarm rings. Until your mother comes and asks you, go, wake up, you have to go for the program. A body in motion, like in the evening you are on your mobile phones, playing games, chatting, whatever, social media. A body in motion, a body on the mobile phone continues to be in the state of mobile phone till the morning, unless you realize, I had to sleep. Unless your father comes, what are you doing on the mobile phone? It's 2 a.m. And then that is the action of force, then you sleep. Similar thing happens with the coil. The coil was at rest. There was no magnetic field associated with the coil, isn't it? See, there is very less number of field lines are linked with the coil. But all of a sudden, this coil which was at rest, what happens? When the bar magnet is set into motion, the number of field lines which is linked with this coil increases. The coil also doesn't like this change. For example, you are running in a particular direction, okay? And all of a sudden, someone pushes you. You have your own inertia of rest, inertia of motion, inertia of direction, isn't it? What is inertia? It is the tendency to oppose this change, isn't it? Now this coil, because it doesn't want the field lines to pass through it, what it does is, it produces magnetic field in the reverse direction. So that means, if I show it with the help of diagrams now, let me keep all the stuff here. I will show it with the help of diagrams now. See what is happening. In the first case, when the north pole is coming closer to the magnet, to the coil doesn't like the approach of the north pole. Okay? So what it does? It produces its own north pole here. And to produce a north pole, you need to know a certain law. The law is this. Remember, whenever current flows in a coil in this direction, the clockwise direction, it generates the south pole. Which pole? Which pole does it generate? And when the current flows in the anti-clockwise direction, the counterclockwise direction, it generates the north pole. Can you remember this? When current flows in clockwise, which pole does it generate? South. And when it flows in anti-clockwise, which pole does it generate? North. Is that fine? Now look at this. Look at this. When the north pole is coming closer, can you tell me what is the direction of the current here? First, click a picture of this because it will get erased. Did you? For that, because I have to show the direction of the motion of the electrons. Yes? See what is happening. When the north pole is coming closer, the electrons are moving like this, isn't it? The electrons are moving like this, yes? Which direction is it? They're going like this, right? So it is the anti-clockwise direction, isn't it? So remember, I just showed you. If this is anti-clockwise, that means north, and if it is clockwise, then it is. Now, very important. This is the direction of the positive charge because current is the direction of the positive charge. Here, the motion is of the electrons. Okay? Now try to understand what is happening. The bar magnet is coming closer to the coil. That means north pole is approaching. The electrons are moving in counterclockwise direction. That means this. Is that fine? So north and north will show what? Repulsion. The coil is not letting the magnet to come closer to it. Why? Because it doesn't want the field lines to pass through it. Is that fine? So when the bar magnet is approaching, the coil doesn't let these field lines to go through them, and due to which it asks its electrons to move in such a way that it opposes the change. The change was north pole is approaching. It doesn't want the north pole to come towards it. So it develops electrons. It asks the electrons to move in a particular way. So that it develops which pole? The north pole. When it develops the north pole, here, this will be the south pole. So it will oppose. Now the magnetic field lines will be generated in this direction. Due to which the original will be opposed. So the motion will be slowed down. And because the electrons are moving, the bulb glows. Is that fine? Now what happens when when the magnet is taken out? Now if this is the case, north is here, south is here, and the motion is like this. See what is happening? When the bar magnet is going away, the field lines which are linked with the coil, are they increasing or decreasing? Yes? When the magnet is going away, the field lines which are linked with this, are they increasing or decreasing? They are decreasing. Does the coil want this change? No, it doesn't want the change. Now because it had accepted, see, understand, very important. Yes? Okay. Initially there was no magnetic field, okay? But once it is inside, it accepted, okay, now it is increasing, what can I do? Now it was trying to oppose it, but it cannot, it doesn't have that energy, okay? But then, now the bar magnet is going away, it is going out. When it is going out, very important, the coil is again seeing a change. First, you start to love someone and all of a sudden you start to hate him. He will be like, what are you doing with me? Same thing is happening here. When the magnet is going away, the coil doesn't like it going away. It doesn't want it to go away. And if you see the direction, see, the coil is observing. So here the coil was in motion. So it will have inertia of motion this time, isn't it? So it will continue to be in the inertia of motion. It will continue to be in motion because of inertia. So what will happen is, the moment this bar magnet is taken away, the coil doesn't like the magnet to go away. So what it will do is, it will generate north pole from this side. Because once it generates north and south will attract. The coil doesn't want the bar magnet to go away. So it will generate north. How will it generate north? By developing current in anti-clockwise direction. Is that fine? So here, see. See what will happen? Oh, I have to remove it. When this bar magnet is approaching, see the direction of the current. Is it anti-clockwise? Yes? And then when it is taken away, see? South. When it is taken away. When this is taken away, now the south pole is here, is it? When the south will go away, the coil doesn't like it going away. It will try to generate a pole such that it opposes the cause. It will try to attract it, and due to which it will develop north pole here, because north and south will attract. Is that fine? So in both the cases, the bulb is glowing when it is in motion. But once you keep it at rest, is there any change when it is at rest? No, there is no change. When there is no change, the bulb doesn't glow, because the coil is at inertia of rest. It is not seeing any change. But if you take it like this, for example, you take it like this, see? You are placing it inside. The magnetic field is maximum. When the magnetic field is maximum, again the same thing. It is maximum, but it is not changing. So the coil is at maximum flux, but that flux is constant. When it is at constant, the bulb doesn't glow. Is that fine? So we are having two cases. One, when there is no glowing of the bulb. The other, when there is glowing. Glowing takes place whenever the flux changes. If the flux doesn't change, the glowing doesn't take place. Is that clear? So Michael Faraday comes up with an equation. He says, so he comes up with an equation, and the equation was this. The equation is this, that the potential or the electromotive force that gets generated, it is equal to the change of the flux per unit time. This is the equation. Whenever the flux changes, EMF or the voltage gets generated. And that voltage will only be generated whenever the flux is changing. If there is no change, if the change is zero, then the EMF will be zero. Is that fine? Is it clear? Fine? But you know, flux is equal to magnetic field times area, isn't it? So in order to change the flux, how can you change the flux? Either increase or decrease the magnetic field, isn't it? Or change the area, right? Yes? Either increase or decrease the magnetic field or change the area, then only you can change the flux. So one way of changing the magnetic field was move the magnet or move the coil. But in some other case, what I can do is, see, first try to copy this. Click a picture of this equation, because this equation is important.
Change in flux
Over change in time. Change in flux over change in time.
and E equals what? E what is the name?
E is the EMF, the electromotive force. Electromotive force. Okay? Is that fine? Now see what is happening, very important. See, something very important. In order to change the flux, magnetic field or the area can be changed. See, if I change the magnetic field, that means I'll take it away or take it closer. Take it away or take it closer. So flux is changing, the bulb is glowing. Or what I can do is, I can increase or decrease the strength of the magnet. See, the strength is here constant. There is no glowing, fine? But the moment I decrease the strength, that means the number of field lines again changes. See what is happening if I change it? See? This is glowing when the magnetic field, although it is inside, but the magnetic field is changing. The strength, the number of field lines which are crossing are changing. The magnetic field here, see, it is faded, but now if I increase it, it will get prominent. If I take it away, see, again faded. No magnetic field, nothing. The moment I start to increase the magnetic field, the bulb is glowing. The moment I start to decrease the magnetic field, the bulb is again glowing. Look at the values here. See, if I am increasing the strength, glow. If I am decreasing the strength, glow. If I am keeping it zero, nothing happens. If I am keeping it at maximum, nothing happens. It is the change of the magnetic field that generates the flux, that generates the EMF. And very important, magnetic field strength can be increased or decreased by motion as well. You can take it away, you can take it into, you can take it away, you can take it close. Is that fine? Clear? And one more thing. As I told you, flux is magnetic field into area. You have to change the flux. So how do you change the flux? First was by magnetic field. Second was by area. Now see, the coil has an area, okay? This coil has an area. But if I increase or decrease the area of the loops, see? When the area is less, it's constant, nothing is happening. But see, if I increase the area, what will happen? Do you see? When the area of the coil is changing, flux is changing. When flux is changing, EMF is generated. The coil doesn't want the magnetic. What is happening when the area is increasing or decreasing? When the area is increasing, more number of field lines are crossing. When the area is decreasing, less number of field lines are crossing. And due to which we are seeing that this coil doesn't like the change. And because it doesn't like the change, the bulb always glows. So that it will oppose the change. Fine? That is the concept. Is it clear? The concept of electromagnetic induction. This experiment, called as the Faradays experiment, was the reason of the new branch, that is the electromagnetic induction. So see, whenever the magnetic field lines are changing, whenever the flux linked with the coil is changing, the bulb will always glow. So you can change the magnetic field or the flux in several ways. First, you can just put it into motion, okay? You can put the coil in motion, okay? Or you can increase or decrease the strength of the magnet. Here you are changing the bar magnet strength. Or what you can do is you can change the area, fine? Or one more thing, if you increase or decrease the number of loops, because number of loops also determines the magnetic field lines which are crossing. See, if the number of loops are increased, see what is happening. See, it is increasing. When there is change, it glows. When there is a particular value, nothing happens. See? Changes, the bulb is glowing. No change, the bulb will not glow. Now I ask you a question. The question is, if both the magnet as well as the coil are moving with the same velocity,
Will not change.
will the bulb glow?
No.
Why?
Because it's constant.
Exactly. So what will happen is, see, if both the magnet and the coil, if both are moving with some velocity, say for example this is moving with velocity v and this is also moving with velocity v. When the velocity will be same, therefore there will be no relative motion. Okay? There will be no relative motion. When there is no relative motion, remember, no change in the flux. Because it will always, the bar magnet will always be here, the coil will always be here. They will not seem to be in motion through each other, and due to which there is no flux. There is no change in flux. Okay? But what if this is moving with V1 and this is moving with V2?
It will be changed.
Yeah, there will be change. So remember, what is important now? It is the relative motion. Which motion? Whenever there is relative motion, not motion, but relative. Relative means one is going away, other is coming closer. One is going away, other is coming closer. If both of them are moving with the same velocities, there is no relative motion. Is that fine? So these are the various cases where we will see the flux changing and due to which the bulb will glow. Is that clear? Is it clear? So let me draw 5 diagrams here and let me ask you in which of the cases will the bulb glow and the bulb will not glow. The first case is this. There is a coil. It is moving with velocity v1 and the bar magnet is at rest, north and south. There is a coil, there is a magnet, the bar magnet is in motion, it is moving with velocity v, but the coil is at rest, okay? The bulb is here, the bulb is here as well. Okay, then we have a coil connected with a bulb. Okay, but the magnet is inside. Then we have a coil which is connected with a bulb. Okay, and we are seeing that this is moving with some velocity. The magnet is here. It is also moving with the same velocity. Okay. Then we have a case where there is a coil and there is a magnet and both are moving with some velocity. And then we have another case where there is a coil, there is a magnet, this is going here and this is going here with velocity v1 and velocity v2. Where do you see the bulb will glow? In which cases? Yes. What about the first case? Will the bulb glow?
Yes.
Why? Because the coil is going towards stronger magnetic fields. Is that fine? Stronger means magnetic field is changing, flux is changing. When the flux is changing, so here it will. Okay? What about this case?
Yes.
Why?
It's going away.
It is going away. Now can you tell me what will be the direction of current here? Yes?
Coming to
See what is happening. In this case, the coil is coming closer to which pole?
no.
Does the coil want north pole magnetic field lines to come? No. So it will develop which pole here? North. So for north to develop, you know what is the direction of the current? Counterclockwise. Counterclockwise means current will flow like this. Very important. Understood?
Yes.
What about this?
Power.
It is going away.
South.
The coil doesn't want it to go away. Therefore, it will develop which pole? South pole. Therefore, the current will flow in this direction. So the direction of current is changing depending on what is happening with the flux. If the flux is increasing, it will develop it in a different way. If the flux is decreasing, the current will, the direction of the current will change. Because the change is such that it opposes something which has produced it. What about this?
Resist.
No, there will be nothing. Why? Because the flux is constant. It is inside. It's not changing. Everything is at rest. No relative motion. Okay. What about this?
No.
Why?
Same.
Yes, because the number of field lines. Yes, there will be some field lines which will be linked, but all the field lines are constant. They are not changing. So there will be no flux here as well. No changing flux. What about this?
Yes.
Yes? Can you tell me? Okay, so yes, it is. But if V1 is more than V2, tell me the direction of the current in the loop.
V1 is more than V2.
Yeah?
It will be north.
Exactly. So it will develop the north pole. So the current will be something like this. Understood? So current is being generated because of the magnetic effects. This is electromagnetic induction. What about this?
Yes.
Yes, again, very good. What will be the direction?
Anti-clockwise.
Why?
Because
Because north is coming closer, it doesn't like the north, so it will develop current like this. Is that fine?
Yes.
Now tell me what about this? There is a coil and then there is a magnet. This is south pole and this is north pole, and this is happening. Tell me.
No.
Yes or no?
yes. No.
Yes. So what will be the direction?
It will be clockwise.
Clockwise. Why?
That's the same. South.
Because see, the south is coming closer. The coil doesn't like the south. It will develop south pole, and for south pole, I told you the sign convention. Clockwise. Is that fine? Do you understand? This is the crux. So this, all of it was given by an equation, and the equation was the EMF is equal to the change in the flux divided by the time. That is it. But this was the magnitude of the EMF. Okay? How much EMF will be generated? How much? This is the equation. But Faraday could not explain the direction. Why is the direction? You know, when I showed you the motion, I showed you that the electrons are moving in different directions. Okay? But Faraday could not come up with this. What are the various directions? For that, there was another German physicist. His name was Heinrich Friedrich Lenz. He gave a different law. The law was to understand what is the direction of the current. Why is the current here in anti-clockwise direction? Why is the current here in clockwise direction? Why is there no current? Why is there current in the clockwise direction? So the direction of this current, which you already know now, was not given by Faraday. It was given by Heinrich Friedrich Lenz, a German physicist who said, write it down, for the direction of the induced EMF, Lenz's law states that the direction is such that it opposes the cause. The direction is such that it opposes the cause which has produced it. See, I'll tell you.
It opposes the what?
It opposes the cause which has produced it. It is like someone is helping you to, someone is feeding you and you are working against him. What did you write? Yeah, from where? So the direction of the induced EMF is such that it opposes the cause which has produced it. See, I'll take this example, you'll understand. Why did EMF generate here? Because which pole was going away? North. Now the coil observes north is going away. It doesn't want the north to go away. So it will work. Going away helps it to produce EMF. But the EMF that is produced is opposing it. It doesn't let the bar magnet to go away. It is producing south pole, isn't it? South will attract the north. So it is doing work against it, isn't it? Try to understand. The direction is such that it opposes the cause. The cause here of producing the voltage was that the north is going away. But you said that the direction is such that it opposes the cause. It will produce south pole, isn't it? South won't let the north to go away. North going away is helping me to produce the voltage. But I'm not letting the north to go away. I'm asking come back. Is that clear? Yes? That is the Lenz's law for the direction of the EMF. And therefore, the equation which was given by Faraday was modified. And the modified equation is this. EMF is equal to negative because it is opposite. Is that fine?
So
the sign here is negative. Why? What is the reason? Because it is opposite. Is that fine? Yes? Should I erase all of it? Yes? This is the concept of the electromagnetic induction. If you can understand this, it will be easy. If you do not understand it, it will be difficult. because this is the basic of this whole chapter. So I am just doing the experimental part so that you can see what is actually happening. Now, I have a question for you. With that, we will stop. Should I erase it? What happened?
Screen closed.
Okay.
Charging.
Now see, there was a question which was asked in IIT. The question was based on the concept of electromagnetic induction. The question was, there is a bar magnet, north pole, south pole. It is falling because of gravity. So I had a bar magnet in my hand and I dropped it. So it will fall. What will be the acceleration with which it will come down? Very good, 9 meter per second, isn't it?
Yes.
But the question was, if there was a coil through which it has to pass and then come to the ground, the acceleration with which it will come to the ground, will it be more than 9.8, less than 9.8, equal to 9.8, or none of these? This is the question. If there is a magnet which has to fall and go through the coil before it touches, this is the ground, okay?
More.
Will it be more or less? Tell me.
Can it go around?
Around means?
It goes up towards it.
No, it will always go inside, through it. It has to pass through it. So it has to go like this.
More.
It will be more.
It has to go like this. North, south, like this.
Will it be
Will it be more or less?
More.
More. Why?
At first it will push it away and then it wants it to go out, so it will accelerate the force.
Okay.
equally?
Equal 9.8? Yes, Hiba?
My answer will be less.
Less.
Increase.
Increase. Yasin, what do you think?
Decrease.
Decrease.
Minus.
Rauda?
Decrease.
Decrease. Yes, Tagreed, what do you think? Equal. Equal? What did she say? Equal? Decrease. Okay, see, understand the concept. If you understood this, then you cannot do this. First of all, is the north pole coming towards the magnet, towards the coil?
Yes.
Does it like north pole coming closer?
No.
What will it do?
It slows down.
It will generate current such that it will generate current, isn't it?
Yes.
It will generate current such that north is developed here, south is developed here, isn't it?
Yes.
So it will try to oppose it, due to which it will slow down, isn't it? So now it has slowed down. It is slowly coming inside, coming. Here, it will, here, when it is completely inside, it will go with 9.8, no problem with that. But the moment it starts to come out, this is north, this is south. What is happening? South is going away. Does the coil like south going away?
No.
Then what will it do?
It changes.
It will change the poles. It will say, no, please don't do this. I will generate north here, south here, reverse. First it wants it to go away. Then it says, no, don't go, please come back. But the moment he comes back, he says, no, go. So there is a proper distance that you have to maintain in a relationship. Isn't it? That's why they say there has to be space, proper space. Don't come too close. Don't go too far away. Just stay at a particular distance that will be good for the relationship to grow. So what will happen? The moment it will come out, this will generate north and this will generate, due to that north, there will be the force of attraction. isn't it? Attraction, will the attraction let it go down with 9.8?
No.
Then?
Yes.
Exactly, that is why Hiba is correct. Is that fine? Yasin also understood, thank God. Is it clear? So it will go slow. Another question. If the magnet has to fall here, from the same height, say here, and this is the ground, the time, say the height is h, okay? The height is h. The time it takes is t, okay? The time it takes to come to the ground is t. Now, if the same magnet has to go through a coil and then reach the ground, the time that it takes, is it more than t, less than t, or equal to t? Yes?
Yes.
Equal.
More!
Which one?
This one.
Is more.
More, right?
Because first it pushes the way.
Because there is some opposition here,
Huh?
there is some repulsion here initially,
Yes.
and there is some attraction here. So more time.
Oh.
This is free.
This one is less.
This one is same. This is t. This takes time t to come down. But this won't take t. It will take more than t, isn't it? This is the concept of electromagnetic induction. Is it clear?
Yes.
Fine? Things like this. Do you know one of the best applications of electromagnetic induction? Have you seen an aeroplane fly? You know what? When an aeroplane flies, very important, electromagnetic induction happens with the aeroplane as well. The North Pole is here of the Earth. If you look at the Earth, North and South. Say for example, aeroplane is here. The magnetic field lines are like this, isn't it? So there is a concept of motional EMF, electromagnetic induction again, due to which when the aeroplane flies, it cuts these magnetic field lines. When it cuts, it will oppose the change, and that change will develop one wing as positive and the other wing as negative. Current flows in the aeroplane. Similar thing happens with your bicycle. Do you know that there are spokes in your bicycle? Yes? Those spokes like this. When, for example, you are riding your bicycle like this, what happens? These spokes cut the magnetic field lines. And when they cut the magnetic field lines, you will be amazed to know that the rim of your bicycle is positive and the center point is negative and the current is flowing. That is how the dynamo charges. While you are doing it, When you stop, nothing happens because flux doesn't change. So there is a concept of electromagnetic induction again. Is that fine? One of the beautiful applications of this electromagnetic induction is a transformer or a generator. I wish I could. Maybe tomorrow, inshallah. Is that fine? Rauda al-Khori is already exhausted. So tomorrow, just go through the concept of a transformer. I'll try to explain it here. Transformer. A transformer. Armada, not armada transformer. A transformer with which you increase or decrease the voltage. Understood? Yeah, I know. We have it in India. You might not be doing it here. It's fine. Thank you.